HVAC control systems are the brain of a building. They automatically measure variables like temperature, humidity, and pressure, and then adjust valves, dampers, and fans to keep spaces comfortable and energy efficient. Think of it like cruise control in a car. Once you set the desired speed, or in this case temperature, the system does the rest. Without proper controls, even the best HVAC design can waste energy and fail to maintain comfort. So, control isn't an accessory. It's what makes an HVAC system smart, responsive, and efficient. Basic control loop components. Every automatic control system works as a loop. It starts with a sensor measuring something important, say the discharge air temperature. A controller compares that reading to a set point, like 55 degrees. Then it tells a controlled device, a valve or damper, what to do. The controlled agent, like water or air, responds to that command, changing the temperature until the sensor sees it's right. This constant measurement, comparison, and correction keeps your system stable, just like a thermostat keeping your home comfortable. In HVAC, this is called a closed-loop feedback system, and it's the foundation of automation. Types of control loops. There are two main control types, open loop and closed loop. An open loop acts based on outside conditions, for example, adjusting a valve based on outdoor temperature alone. It assumes conditions stay predictable, but in reality, they rarely do. Closed-loop control, on the other hand, responds to actual measured results, such as the real air temperature leaving a coil. That makes it more accurate, stable, and energy efficient. In modern HVAC systems, closed-loop control is the standard because buildings aren't static. They breathe, change, and demand constant adjustment. Control points controllers use two types of signals, binary and analog. Binary means on or off, like a fan switch or a damper position sensor. Analog signals vary continuously, for example, a 0 to 10 volt signal that tells a valve to open 45%. Binary is simple but limited. Analog allows precision control. Understanding these signals is key to reading schematics and troubleshooting modern control panels. Control actions are how a controller reacts to changes. Let's walk through the main control types used in HVAC systems. A. Two-position or on-off control. The controller switches fully on or off with a small temperature band, called the differential. Used in thermostats and frost protection, simple, reliable, and inexpensive. Easy to understand and troubleshoot. Downside, temperature swings, less precise control, and equipment wear. B. Floating control controller sends open more or close more pulses to actuator. Actuator position floats based on accumulated pulses, used in older pneumatic systems or low-cost dampers. C. Proportional control. The output is proportional to how far you are from the set point. Closer you get, smaller the change. The basic equation is output equals Kp times error. Here, Kp stands for proportional gain. It represents how sensitive the controller is to the error. A higher Kp means a stronger, faster response. A lower Kp gives a smoother, slower adjustment. Now, let's talk about throttling range, also known as the proportional band. It's the temperature range over which the control device, like a valve or damper, moves from fully closed to fully open, or from 0 to 100%. This defines how tight or wide the controller reacts to temperature changes. In short, proportional control provides steady, smooth regulation, but fine-tuning the gain and throttling range is key to avoiding oscillation or sluggish response. That's why we add integral action. D. PI control, proportional plus, integral adds. Integral action to proportional control. Integral term accumulates error over time and adjusts output to eliminate offset. The equation is output equals Kp times error plus Ki times the integral of error over time. Here, Kp is the proportional gain. It sets how strongly the controller reacts to the current error. Ki is the integral gain. or 1 divided by the integral time constant, Ti. The term integral of error means the controller looks at the accumulated error over time, not just the present difference. Most commercial HVAC systems use PI control. It's stable, accurate, and energy smart. E. PID control adds derivative action that responds to the rate of change of error, providing anticipatory control. The equation is output equals Kp times error plus Ki times the integral of error over time plus Kd times the rate of change of error. Here's what each term means. Kp is the proportional gain. It reacts to the current error. Ki is the integral gain. It looks at the accumulated error over time to eliminate steady-state offset. Kd is the derivative gain. It predicts future error by measuring how quickly the error is changing, or the rate of change. Together, these three actions balance speed, accuracy, and stability. It reacts to how quickly conditions change, reducing overshoot and speeding up response. Best for systems needing precise, stable control. F. Time proportioning or pulse width modulation. Turns on and off rapidly within a time cycle. For example, on 7 seconds, off 3 seconds in a 10-second cycle. Used for electric heaters or staged systems that can't modulate smoothly. Controller technologies. There are 3 main types of HVAC controllers. Pneumatic systems use compressed air to move valves and dampers. Old school, durable, but high maintenance. Analog electric controls use electrical signals, faster and cleaner but less flexible. Modern systems use microprocessor-based controls, or DDC, direct digital control. These use software logic, allow remote monitoring, self-diagnosis, and adapt to changing loads. Today, DDC systems dominate the industry, bringing smarter control, fewer parts, and much higher energy efficiency. Control devices and actuators. Controls need the right hardware to work effectively. Dampers. Opposed blade dampers offer smoother modulation. Parallel blade dampers open fast, perfect for isolation. Remember, even closed dampers leak, so use low leakage models where tight shutoff matters. Control valves. Two-way valves save pump energy in variable flow systems. Three-way valves maintain constant flow in older or constant volume designs. Select the right flow characteristic. Linear for steady pressure, equal percentage for variable systems, and quick opening for simple on-off. Flow sensors, pitot tubes, ultrasonic meters, or differential pressure sensors all help verify that flow matches design intent. 3 control levels. Unit level control controls individual equipment, e.g. air handler, VAV box. System level control coordinates multiple units for efficiency. Building management level, central monitoring, alarms, data logging for entire building. Unit level control focuses on individual HVAC equipment, like air handlers, rooftop units, or fan coils. Each unit has its own controller that handles safeties, alarms, and set points. For example, a VAV air handler might include multiple control loops, one for discharge air temperature, one for outdoor airflow, one for static pressure, and even one for building pressurization. Each loop senses, decides, and acts automatically, keeping the equipment stable even if communication with the building system is lost. System-level control is where the orchestra comes together. Imagine each unit controller as a musician. The system controller is the conductor, coordinating timing and balance. It manages modes like occupied, unoccupied, and morning warm-up, making sure chillers, boilers, and fans all work together. For example, it can ensure a cooling tower and boiler don't run at the same time, or that VAV boxes and air handlers adjust together. This coordination improves comfort and cuts wasted energy, turning multiple machines into one intelligent system. Examples of system-level control: chilled water, VAV system, coordinates air handler, terminal units, chiller, and boiler. Packaged rooftop, VAV system, Integrates all functions in one unit. Fan coil, chiller system. Uses outdoor air reset and changeover deadband, 15 degphi, to save energy. Water source heat pump system. Maintains loop temperature between 60 degphi and 90 degphi using tower and boiler. A building automation system, or BAS, ties everything together. It's the central nervous system, collecting data, logging trends, handling alarms, and allowing remote access. Modern BAS platforms use open communication protocols like BACnet, LawnWorks, or Modbus, so devices from different brands can talk to each other. Through dashboards and analytics, the BAS gives operators total control and insight, from air handling to lighting to energy metering, all in one place. Even the best controller won't work well without proper tuning. Tuning means adjusting how strongly the controller reacts to errors. If it reacts too aggressively, the system overshoots or starts hunting around the set point. If it's too slow, comfort suffers and energy use increases. The goal is balance, quick enough to respond, but steady enough to stay stable. Technicians often use trial and error or Ziegler-Nichols methods to find the right settings. Today's digital controllers even include auto-tuning algorithms, making the process faster and more accurate. When tuned correctly, a control system maintains ideal comfort with minimal energy use, the ultimate goal of HVAC automation. Here's the big picture. Every HVAC control system follows the same logic: measure, compare, correct, repeat. Closed-loop control keeps comfort consistent. PI and PID controllers balance speed and stability. Microprocessor-based systems make everything smarter, faster, and more efficient. And when integrated into a building automation system, they create a connected, optimized, and energy-conscious building environment. Mastering these fundamentals is your first step toward becoming fluent in modern HVAC controls. Thanks for watching. Don't forget to like, subscribe, and continue your journey toward HVAC mastery.